Today, we're going to do something a little different. We're going to deconstruct the digital plumbing of our entire world by, get this, reverse engineering a university final exam. We're going to see how the systems that literally run our lives are built, right from the ground up. Let's dive in.
I mean, just think about that for a second. 25 million packages every single day. That's not just organized, that's a borderline miracle of information management. How is that even possible? How do you keep track of that much stuff, moving through that many places all at the same time? Well, the answer isn't magic, it's data.
You see, every great system starts with a plan, a blueprint that lays out every single connection before anyone writes a single line of code. And we found the perfect example of this whole process in a pretty unexpected place: the final exam for a Fundamentals of Database Systems course.
So, our first step is all about that initial plan. You know, before you build a house, you have to know where the rooms go, how they all connect, and what each one is for. It is the exact same thing with data.
So here's the challenge these students were given. They have to design a tracking system for UPS. You've got to think about the items themselves. Each one has a unique ID, a weight, a destination. Then you have the journey itself. It starts at a retail center. It moves through different transportation events. Every single piece of this puzzle needs a home.
And the tool for that job is this: an entity relationship diagram, or you'll hear it called an ERD. The absolute best way to think about it is as an architectural blueprint, but for information. It shows you the key things, we call them entities, and exactly how they relate to one another.
And here it is. This is the solution from the exam. Now, what's so cool about this is how it takes that wall of text we just read and turns it into a clear visual map. You can actually see shipped items right there in the center, and you can see how it connects to a retail center and to transportation events. It's the entire system on a single page.
Okay, so you've got your blueprint. Awesome. But now you have to make sure the data you actually put into that structure is clean, efficient, and logical. And that brings us to our next step: cleaning up the mess.
The exam gives us this perfect example of what not to do. Just look at this table. In one single cell, you've got multiple courses just crammed in there. It's messy, it's really hard to search, and it's incredibly inefficient. This is a classic data problem. So the process of fixing this is called normalization. Now, it sounds super technical, but the goals are actually really simple. First, you get organized. Make sure every box has only one thing in it. Then, you get efficient by getting rid of information that's just repeated over and over. And finally, you get logical. If a piece of info doesn't belong there, you move it to its own table where it does. And this right here brilliantly illustrates the result. On the left, you've got one giant, clunky table. But on the right, it's broken into two clean, logical tables. One just for students and one just for colleges. And they're linked together by a simple ID. Now everything has its proper place, and that makes the whole system way faster and more reliable. Okay, and now for the real payoff. We've got a solid blueprint, we've got clean data, now it's time to actually use it, to ask questions and get some answers.
In the academic world, a question you ask a database can look, well, like this. It's called relational algebra. I know, it looks like a crazy math problem, but all it's really asking is, hey, from that employee table, can you select all the people whose gender is male, and then just show me their name and gender? Now, in the real world, we translate that algebra into a language called SQL, that stands for Structured Query Language, and it reads almost like a plain English sentence. Select the name and gender columns from the employee table where the gender is M. These are kind of like the magic words that let us talk directly to our data. And just like that, boom, the database gives you exactly what you asked for: a clean, simple table with the names of all the male employees. You ask a precise question and you get a precise answer. That is the power of a really well-designed system. But what if you need to ask a more complex question? This line of code from the exam is asking for information that lives in two different places: the employee table and the department table. It needs to combine them. So how do we do that?
Well, to do this, SQL uses this incredibly powerful command called a join. This command is the key to everything. It selects info from the employee table and tells it to literally join with the department table, using the department ID as the connecting piece. This is how we connect the dots between all of our neatly organized tables. And here is the combined answer. We now have a list of employees right next to their department's name. So even though this information was stored separately to be efficient, the join just brings it all together in one useful view. And hey, notice that last entry. Mustafa has a null value because he isn't assigned to a department in our data. That's a perfect example of what a left join does. So let's just zoom out for a second. We've gone from a blueprint to organizing data to asking it questions. This fundamental process isn't just for some university exam. This is the foundation of almost every single digital service you use every day.
The exam even touches on what's next. See, everything we've talked about so far is the traditional relational or SQL database. It needs that strict blueprint, that schema. But there's also a newer approach called NoSQL. It's schema-free, way more flexible, and it's often used when you need massive speed and don't want the complexity of that rigid structure. Both have their place.
So it all comes back to the blueprint. From tracking packages to your social media feed, it all runs on these fundamental principles of design and organization. The technology is going to keep changing, for sure, but that need for a smart plan, that will always be there. The only question is, who's going to be drawing the next set of blueprints?